Hey everyone, welcome back. In this video, we're going to be going over part one of the final review out of all three. This part covers exponential and logarithmic functions review. Let's hop into it. So the basic idea starting off with exponentials and logs is that they're inverses. So an exponential function can be undone by a log function and vice versa, they're inverses. Since they're inverses, there's also ways to convert between exponential form and logarithmic. So it might be helpful for you guys to remember the following. I don't know if I want to call it like formula, but the conversion, I suppose, where we have log with some certain base. So this is just like a reminder off to the side. When you have a log with any base of some sort of like input value, that is equal to the exponent, and if we roll our logs, we can convert that to exponential and say, well, then that's equivalent to b to the x is equal to y. So we're going to be using this fact an awful lot. And you'll notice, like, for number one, part A, it wants us to rewrite this logarithm, because it has the word log, as an exponential. So it needs to have an exponent, which would be right there. And we just need to rewrite it. And notice that the exponent was on the right-hand side. The base of our logarithm becomes the base of the exponent. And then the input of the log, the thing inside, sometimes the parentheses, sometimes not, becomes what it's equal to. So if we were going to convert problem number one, right, we could say the base of the log is 3, raising that to the 4th power is equal to 81. And you can verify this with the calculator. Punch it in. 3 times 3 times 3 times 3 is in fact 81. So we're going to keep using this fact over and over and over again. Number 2 is already in exponential form. The reason I know this is because I can see that straight away there's an exponent, there's a base part, and then there's also like something that it's equal to. So if I'm going to convert this into a logarithm form, it's really important that we remember the base of the log has to equal the base of the exponential. So this is going to be log base 5. The argument is 15,625. And it is equal to the exponent of 6. And a great thing to keep in mind when we're doing these is if you want to double check your work and see if, like, oh, did I do that right? I'm not entirely sure. Roll your log. Say, take your base of your log. Is 5 to the 6th actually 15,625? And the answer to that would be yes, because that's what we started with. So there's a lot of ways that you can self-assess and see if what you're doing matches up with what you're trying to achieve. Now, the next problem, C, it says e to the 5x equals 12. So it might be a little weird, but let's just highlight what the base of our exponential is. The base is e. E is Euler's number. It's like 2.8, 2.817, 2.718. I should probably Google that, honestly. 5 to the x, and then its argument is equal to 12. So if we're going to convert this to a log, right, the base of the exponential needs to be the same as the base of the logarithm. Move on. Oops, I meant to erase. Right, we're trying to use this formula right here. So we're going to say, all right, this is going to become log base e. The argument is going to be 15,625, and it's going to be equal to 6. Now, something that you're going to want to remember is that a log with a base of e is actually the natural log. So that's ln. So this is the natural log of 15,625 is equal to 6, right? Because log base e is equal to the natural log. And that fact's going to come in handy because we can see part D says to convert the natural log of x plus 1 equals 6. So this is really log base e, if you're more comfortable with that. X plus 1 equals 6, and you can use this to convert and roll your log. We can say that this is going to become e to the 6th is equal to x plus 1. Let's move on to the next. So solving exponential unlog equations, make sure we're checking for extraneous solutions whenever necessary. So usually when we're working through these, we can see we have log base 9 of x equals -2, and I can't really do much. I cannot solve for x. I can't solve for a specific value of x when it's in this log form right here. So I'm going to convert to my exponential form. It's going to give me 9 to the -2 is equal to x. And although x is equal to a number right now, I need it to be like a specific number. 9 to the -2 doesn't really tell me anything. So by properties of negative exponents, this really becomes 1 over 9 squared is equal to x. And then 9 squared, of course, 9 times 9 is 81. So 1 over 81 is equal to x. When we have a problem like part B, says 2 to the 3x equals 120, that's cool because it's already in exponential form. The trouble with this, though, is that our x is up in our exponent. So we're going to need to get that down. And you could take the log of base 2 of both sides as inverse operation, since logs and exponentials are inverses, or you could just convert this back into a logarithm. So it's going to have the same base. So this is going to be log base 2. The input is going to be 120. And it's going to be equal to the exponent 3x. Now that we have this, we have 3x is equal to something, and it's pretty close to solving for x. So what we're going to need to do here is put this argument, log base 2 of 120, into the change of base formula. So we're going to need to use change of base. And the reason we're going to need to use change of base is because most calculators won't actually tell you what this number is equal to. Log base 2 of 120 is equivalent to some numerical value. So change of base says that if you have log base b of, I don't know, a, change of base says you're going to put log of a on the top, log base 10 of a, and log of the base on the denominator. So if I use change of base, this entire argument becomes log, I always say the big number goes on top, log of 120 divided by log of 2, and this is still equal to 3x. And then you're going to want to grab a calculator or open up calculator on Desmos or Google or whatever. They'll all do them for you. And do the log of 120, just regular old log, 120, divided by log of 2. And you get that number is equivalent. I'm going to erase my change of base here. That number is equivalent. So then we end up with, it's about 6.9 is equal to 3x. And lastly, to solve for x, we'll just divide both sides by 3, giving us x is approximately, excuse me, 2.3. Boy. Oof. Okay. I'm going to change my color for part 3 just in case, because I was running out of space. So now part C of number 2 is almost exactly the same as part B. It's just one step more complicated. Notice that initially we had like a base raised to an exponent equaled something. And the only difference between this problem and the others, one, they're on the other side. So that's kind of tricky, but we still have a base. We still have an exponent, and we still have it equal to something. But the tricky part is now we have this 2 in front of it. So in order for this problem to become the same as the other, I have 2 times 10 to the 4t is equal to 800. And I just want to simplify this a little bit. So in order to get on the same page, we're going to need to use our inverse operations of dividing both sides by 2. And when we do that, we end up with 400 is equal to 10 to the 4t. Now we're back to where we started. So we can convert this to log form, right? This is going to become log base 10 of 400, and that's going to equal our exponent 4t. We're going to have to use change of base formula again. So that's going to become log of 400 divided by log of 10 is equal to 4t. And if you use your calculator, figure out what log of 400 divided by log of 10 is, you're going to get about 2.6 is equal to 4t. Then we divide both sides by 4. And you'll get t is approximately 0.65. 0.6505, oops, so on and so forth. And lastly, this final problem is log base 4 of x plus log base 4 of x minus 6 is equal to 2. And I'm actually going to move on to another screen because this one has a little bit more work involved with it. And we all know that I write way too big for that. So for the next problem, I'm just going to rewrite it and oops, or maybe just mark in green all over the place. Yep, here's a blank space for me to work. So our problem is log base 4 of x plus log base 4 of x minus 6 equals 2. So this one's tricky because the left-hand side, I'm sure you're all kind of thinking, wow, that's a lot. This entire side can be condensed. And the properties of logs are just like the properties of exponents, right? If you have something that is being added, you can condense it by multiplying. If you had something that was being subtracted, you could condense it by division. So right now we have addition, and we can convert and make this expression more compact by rewriting it in terms of multiplication. So if I do that, what's going to happen is instead of adding our 2 logarithms, we're going to convert it down to one single log. Notice that they both have log base 4, log base 4. That's important. So I'm going to rewrite log base 4 just one time though. And then inside the parentheses, we're going to multiply instead of add. So we're going to have x times x minus 6. So instead of adding, we now change the operation to multiplication to simplify our logarithm. And this is still equal to 2. Now, do as your intuition tells you. You're going to distribute these values. You're going to end up with log base 4. X times x is x squared. X times negative 6 is negative 6x equals 2. So now we're back to one of the problems that we've worked with before. Log base 4 of x squared minus 6x is equal to 2. To solve this guy, we're going to convert to exponential form, which says 4 squared is going to be equal to the values inside. 4 squared is 16. And whenever, remember, our goal was to solve, and whenever we're asked to solve for something that involves an x squared term, a quadratic term, anything that has this, and the objective was to solve, think of your favorite F word, favorite mathematical F word, I should say. Factor. So we're going to need to factor this. And when we factor things, we need everything moved onto one side. So I'm just going to subtract 16 from both sides. I'm going to get 0 equals x squared minus 6x minus 16. And in order to factor this, I need to determine what two numbers multiplied together give me 16, but, well, negative 16, but add up to negative 6. So that would be negative 8 and positive 2, because negative 8 times positive 2 is negative 16. But negative 8 plus 2 gives us negative 6. So if I factor this expression, it now becomes 0 is equal to x minus 8 and x plus 2. These two expressions are equivalent. And by the zero product property, setting each factor equal to 0, you get x is equal to 8 and x is equal to negative 2. Now, what we haven't done so far is we've got to make sure that we check for extraneous solutions. So especially since we have two, you have to check your solutions and make sure that they're not extraneous, meaning that they don't give you a false answer, that they're not a lying solution. So you have to check it in the original problem. So we're going to see if log base 4 of our numbers plus log base 4 of our number minus 6 is equal to 2. And I like to put parentheses around the values that I'm going to check. It just reminds me what I'm actually looking for. It makes it a little bit easier. So I'm going to try x equals 8 first. I plug in 8 everywhere. I end up with log base 4 of 8 plus log base 4 of 8 minus 6 is 2, and that is equal to 2. And now in order to solve this, we are going to have to use that same property that we did earlier where we combine them. They're both log base 4 and they're both addition right now. So this becomes log base 4 of 8 times 2 equals 2. That's really log base 4 of 16 is equal to 2. And to verify that this is true, convert into exponential form. Is 4 squared actually equal to 16? And since 16 is equal to 16, then x is equal to 8 is one of our solutions for sure. Definitely a solution. It's a real solution. It is not extraneous. Now we're going to repeat the process, but for x is equal to negative 2. So instead of 8, we're seeing if negative 2 gives us the same information, if it gives us also a true statement. So we're checking out if negative 2 and negative 2 work. Doing so gives us log base 4 of negative 2 plus log base 4 of negative 8. We want to know if that's equal to 2. Now, here's where we have an alert, okay? Alert, If we have a negative input in our calculators, we can never have a negative input inside of a logarithm. And the reason for that is because our logs look something like this. Our logarithm graphs, they have vertical asymptotes and they look like this, okay? And they never go past that asymptote. And if we had something past that asymptote, that would be like a negative input, like something over here. That's not on our graph. It's actually undefined. So if you were to go and check before you proceed any further, if you were to check like what log base 4 of negative 2 was, if you forgot to use the properties of logs to convert them, right? Change of base would say that you have like log base 10 of -2 divided by log base 10 of 4. And if you put this in your calculator, it's going to say domain error or undefined, because we just don't have negative inputs for our logarithms. You can have, like, this is not allowed. You can have a negative base. You can have it equal something that's negative, but the input of your logarithm can never be negative. So x is equal to -2 is extraneous. Careful. That's something you'll want to remember, is you can't have a negative input for a logarithm. Okay. Justin graphed f of x is equal to log base 4 of 7x on the coordinate plane. He then graphed g of x is equal to negative f of x minus 2 plus 7. So which of the following describes the transformation from f to g? And I always like to remind myself, like, we start at f and then we change it to g of x. So it was log base 4 of 7x, and then I noticed that g of x has a negative in front of it, x minus 2 plus 7, and we're talking about transformations, which means we're going to want to keep in mind the following. Our transformations for anything really would be like a times our function of x minus h plus k. We've always had these things in place, and the a value was always going to tell us whether or not we were stretched. If we were stretching, compressing, and this is vertically, or reflecting our graph. Our h value is next to the x, so we never trust it. Our h value is always opposite what we think, but h always told us the horizontal shift, and k always told us the vertical shift, up and down. That's why I spell it wrong. So looking at this graph, well, I shouldn't say graph, this equation, f of x has some of these elements embedded into it. It has a negative in front, it has x minus 2, and it has plus 7 on the outside. So we know that a negative value is going to tell us straight away that that is a reflection across the x-axis. So let's take a look and see. Reflected over the x-axis, reflected over y, definitely not B. Reflected over y, definitely not C. D, reflected over x-axis. Okay. The x minus 2 right here is going to tell us that we are shifting our function. Remember, opposite of what your x says, never trust them. We're going to move right 2 units. So if I'm looking at A, it says 2 units to the left. A is already out. So D says we have to keep checking. Reflected over the x-axis translated 2 units to the right, so that's good. And then we better just make sure that the plus 7 tells us that we're going to shift it up 7 units and make sure that that lines up with option D. And it's 7 units up. Perfect. So the solution for number 3 is D, based on what we know about our reflections, our transformations for any function. It could be a log function, it could be an exponential, it could be a trig function, it could literally be any function ever. These things will always hold true. All right. So determine which of the following represents exponential growth or decay. Circle the correct answers. So what we need to remember here is when we're talking about growth, growth is like the graph on the bottom left in orange. Growth has a base larger than 1. And for decay, like the graph on the left, where it's decreasing all of the time, we have a base between 0 and 1. So just because you have a negative base does not mean that you have decay. It just means you have a reflection there, but base has to be less than 1. So if we're looking at all of these functions, we need to just determine the base. And you might have forgotten the common form for an exponent, right? Just like we were talking about those exponentials. It would be y is equal to a times b to the x minus h plus k. Notice that we've got our horizontal, we got our a, we got our k, right? It's important right now, if we're determining growth or decay, we're only zooming in and only focusing on the base to the exponent, okay? The base is the one next to the exponent. So here in this first problem, I have the base is equal to 1/4. And since the base is less than 1, it's decay. For B, our base is 4. And if my base is equal to 4, then that's definitely growth. C is where it gets a little tricky, because you might observe and look at it and be like, okay, the base is E. What the heck is E? You could even type it in your calculator just to see what E is. And E is like 2.718, right? So you could say, oh, the base is E. 2.718. But what we have to be really careful about is that we have a negative exponent. So if you have a negative exponent, hold on a second and rewrite the problem. If you have a negative exponent, rewrite the problem so that there are no negative exponents. So if you ever encounter a negative exponent, rewrite your problem. By properties of exponents, this is going to become 1/e to the x, but since the numerator is 1, it's just 1/e to the x. And now we can see clearly that the base is 1/e. That's between 0 and 1. So instead of it being growth like we initially thought, it's actually going to be decay. Option D has the same idea, right? Looking at it, I'm like, okay, cool, my base is 4, but I have this negative exponent here. So I have to rewrite this. Negative exponents means we're going to take the reciprocal. So this is going to become 1/4 to the x. Now my base is 1/4, which means that I have a decay. And E, I have 1/4 to the negative x, even further. So you might be thinking, aha, I got you, decay. Psych! What we're going to need to do is make sure we incorporate that negative exponent. We don't want negative exponents when we're talking about growth or decay. We need it to be positive. So this is going to become f of x is equal to the reciprocal, 4/1 to the x. And 4 is larger than 1, 4/1. So that means we have a growth. All right, a cup of coffee is placed on a kitchen table. The temperature in degrees Fahrenheit of the coffee is modeled by this equation. F of x is equal to 76 plus 120e to the negative 0.75x, where this should say x represents time in minutes. Which of the following are true? The temperature of the coffee is increasing. Can eliminate that straight away. You know, if you pour a cup of hot coffee into a cup, it's never going to get hotter. Our cup of coffee is actually going to slowly decrease like this. So it's definitely here. I should probably, right? If we think about this, like the x-axis is time, and the y-axis as temperature. We know at time is 0. At time is 0 right here. It's going to be coming straight out the coffee pot. And our graph, it's going to slowly decrease over time. So that's what we're trying to figure out. The x-intercept or the y-intercept is the next two statements. So let's think about this. If the y-axis is temperature, in order for us to have like an x-intercept, right, that would have to cross the x-axis somewhere. That would mean that the temperature is equal to 0, right? The temperature is equal to 0 degrees Fahrenheit, and the freezing point is 32 degrees. So does a cup of coffee ever get frozen just from sitting outside in a room temperature house? No, it's never going to have an x-intercept. That just doesn't make sense. Our cup of coffee never gets that cold. It gets like not hot. It gets about room temperature, maybe a little bit less, but it's never going to freeze. You don't leave out a cup of coffee and then suddenly it becomes iced coffee or frozen coffee. Otherwise, Starbucks would be out of a lot of money, you know, for their iced coffees if we could just set out our coffee and it would become iced later. So that doesn't make sense. But the y-intercept of the function would be somewhere on the y-axis. And we know, like, hey, that makes sense. When the temperature is 0, like how hot is it coming out of the coffee pot? That would be the y-intercept. And the way that we could mathematically solve for a y-intercept is set x equal to 0. Notice that even in the equation, it's 0. So if we plug in 0 to our function, so we have f of 0 is equal to 76 plus 120 times e to the negative 0.075 times 0. If we plug that in, anything times 0 is just 0. So we have 76 plus 120 times e to the 0 power. But we know anything to the 0 power. Anything. It's a multiplicative identity. Anything to the 0 power is really equal to 1. So we actually end up having, this is 76 plus 120 times 1. And now we can see what the temperature is at time is equal to 0. It's going to be 76 plus 120, and that is 196 degrees. So when your coffee comes out, the initial temperature is 196 degrees. So D is definitely a true statement, and it's also the y-intercept, right? Because the y-intercept is when it comes straight out of the coffee pot, the initial temperature of your coffee is 196 degrees. And since we figured out once we set x equal to 0 and we got that value, clearly it wasn't 120, so we can get rid of option E. And the last question says the temperature of the coffee approaches 76 degrees over time. And that just really asks us to figure out, oops, I thought it was highlighting. What is this asymptote? Because exponential functions have asymptotes with them. Let me change this to not dots and dashed line instead. Exponential functions have asymptotes, and that is based on the vertical shift of our function. Now, normally we have y is equal to a times our base. So here's a times our base of the exponent, x minus h, if there was any x's and h's, plus k. Plus k. If we were going back to our original equation of, how should I put this? Y is equal to a times our base to the x minus h plus k, right? And we have those transformations where a is vertical stretch, compression, or reflection. B is just the base of our exponent. X minus h tells us the horizontal shift, and k tells us whether it's moved vertically. And if we're thinking about exponential growth or exponential decay as a function, right? Here's decay. There is an asymptote, or even if it's growth, there's an asymptote. And that is determined completely by the vertical shift up and down. That's determined by k. So we just have to figure out, well, what is k in our equation? Looks like k is 76. So, oh my gosh, would you look at that? Our temperature of the coffee approaches 76 degrees over time. That's also true. And that makes sense, because remember, if you leave a cup of coffee out, it's going to be like maybe room temperature slightly less. It's a little cool. It feels very cold compared to 196 degrees, and that seems pretty reasonable. So the temperature that coffee or anything that's hot will approach is always going to be the k value given in your function. Okay, let's see. Match each graph with its equation. So what we want to do here for this is I've got log base 2, log base 3, log base 4, log base x, is we want to look for some key points on all of our graphs. So some of us might be like, all right, cool. Let's look at the first x-intercept, or just the only x-intercept. And this is the point 1, 0. Cool. Right here is also 1, 0. Cool. Right here is also 1, 0. Great. And right here is also, gosh darn it, 1, 0. Right? So although that doesn't help us decide which graph is which, because they all have the same point, which is a little bit of a bummer. However, it does tell us that all log functions, all log functions pass through 1, 0. And I should say like all like basic log functions. And really what I mean by that is like all parent log functions pass through 1, 0. If they have a horizontal shift or a vertical shift, or even a vertical stretch, then that number will be changed slightly. But all basic parent log functions pass through 1, 0, which will be helpful in the next question. Then we have to remember that we have that one formula, that one property, that the base of any logarithm to the first power is the base, right? The base, if I set this equal, if I set this equal to 1, 2 to the 1 should give me 2. So any log function right here is going to go through that point 2, 1. So I want to make sure and see if I can find 2, 1 in any of my graphs. And sure enough, graph B goes through the point 2, 1. So B is log base 2 of x. Moving on to the next function, we have log base 3. Again, 3 to the first power is always going to be 3. So that means I'm going to go through the point x is 3, y is 1. So in which graph do we have x is 3 and y is 1? I just did a quick scan at x is 3 and I found out that graph D goes through the point 3, 1. So graph D is going to be log base 3 of x. Same pattern holds true for log base 4, right? 4 to the first power is always going to be 4. So that means I have 4, 1 as a point on my graph. And luckily, 4, 1, right? That's right here on graph number A. So graph A is going to be log base 4 of x. Oops. And lastly, when we have a log without a base, the base is 10. That is the standard log function, is log base 10. This is, you could throw in a little 10 right there. That means 10 to the first power is always 10. That means we're going to go through the point 10 comma 1. And look at here. That point is 10 comma 1. This means that this is log base 10 of x, or just log. Just regular old log of x. So when you're looking to determine logs with different bases, the base to the first power is always a coordinate on your graph. So look for base comma 1, and that should be where your graph is going through. And lastly, match each graph with its equation. More log functions, right? We have the natural log of x plus 2, the natural log of x minus 2, the natural log of x, and 4 times the natural log of x. Remember that the natural log is equal to log with base of e. And we just discovered in the last problem is that basic, like parent functions, go through the point. Parents go through the point 1 comma 0, right, from all of those other graphs. So I can see that if I'm going through each graph, this point right here, the x-intercept is 1 comma 0. Part B, that graph is also going through 1 comma 0. Graph C is not, it's actually going through negative 1 comma 0. And graph D is also not as well. That's going through the point 3 comma 0. Okay, so that tells me right away that this A function and B function do not have any horizontal shifts or vertical shifts. And log base n is going to be log base e. So that means the point e comma 1 is a point on the graph. And if you don't remember, e is 2.718. So we're really looking for the point about 2.7 comma 1 on any graph. And if we're looking at graph A, for instance, here's 3. So 2.7 is like maybe here-ish. Oh my goodness, that lines up with 1. So graph number A should be natural log of x, because it goes through the point 2.71. That's this point right here. Graph B, it still goes through 1, 0, and it looks a little stretched. It looks a little thin here. So if we're looking at graph B, it still goes through 1, 0, but the whole graph itself is very stretched. It's not looking the same shape as this one. It's steeper almost. And what happens when we have a steeper graph just means that we have a vertical stretch in front of it. So that means we have something like maybe 4 in front of it. So graph B is being multiplied by 4. There's no horizontal shift. There's no vertical shift because it still goes through the point 1, 0. But it has been stretched vertically, making it steeper. Then we have to decide, okay, well, what happened to graph C? Graph C should have went through the point 1, 0. Oops. It should have gone through the point 1, 0. However, this graph moved over 1, 2. It moved over 1, 2 to the left. It moved left 2 units. Is there a graph that tells us it's moving left 2 units? Oh my gosh. Would you look at that? X plus 2 really means to move left 2 units from that original point 1, 0. So there we go. And then we can make that same comparison with it should, graph D, it should have went through the point 1, 0. And what happened here is it moved Here's 1, here's 2. It moved to the right 1, 2. It moved right 2 units. And that can be represented by ln of x minus 2. Remember, opposite of what you think. So remember that all of your log functions go through the point 1, 0, unless it has a horizontal shift or vertical shift. If it's stretched and just stretched, none of the other combinations of those, then it's still going to go through the point 1, 0. However, if it's stretched, it's going to be steeper. If it's compressed, it's going to be not as steep. If our function was compressed, it won't be as steep. So, and I believe that concludes part 1 of the review. Yep, part 1. So I hope you're studying. And I'm gonna go ahead and end this right here.